Now here is a little postscript. If this was a modern course, which is not, we would, I'm teaching a very old stuff. I would say, these indices, they're so stupid because they can be any letter. Mathematicians even don't write them. They write them in some way that it's impossible to comprehend. They invent some stupid notation. There's all indices. Physicists and engineers write them in indices that generalizes Levi-Civita tensor. But this is just arbitrary letters. So why am I writing these stupid letters and I'm trying to figure out what's good about this? Why don't we just draw this? That turns out to be beautiful. Now we are classifying all possible Lie groups, and what do they have satisfied? They have to satisfy two properties. This is structure. This is a particular matrix representation in your particular problem. You care about standard model or something. But this is intrinsic. This is generalization multiplication table. It has two properties. It's fully antisymmetric. I showed that here. And it has to satisfy Jacobi relation, which says that if you multiply it in three possible ways, they have to be consistent. And that can be solved. What are all possible structure constants? So in 3 dimensions, the one for babies, it's Levi-Civita. But if you care about superstring, then, it might be E8. It might be very complicated and complex structure constant, but we know all possibilities. And my objection right now is I hate writing all these stupid indices. They're dummies. So what do we do? Do the following thing. Whenever you see a structure constant, replace it by a picture which has, there is something with 3 legs or 3 claws if you're thinking of, birds walking over sand. And then you realize I don't actually have to write these letters I, J, K. The only thing that matters is position. On a piece of paper. I can draw this picture and you can stick any letters you want to it, including Hebrew if that's what you must do. Now what's Jacobi relation, or Jacobian, sorry, he was German, Jacobi relation. You take this picture, you draw this, and it says you have to sum over an index here. You have to sum over m. That's obtained by joining the line between 2 vertices. And then it says, multiply them in one order, that's this, or multiply them in the other order. So I keep the same place in the paper here, and I just interchange them. And it says, that's this thing here, but when you draw it, it looks like that picture. And once you understand this kind of picture, you never need to put this stupid letters, dummy indices again. You can do all calculation in what I call Birdtracks. So this is it. Yeah, Birdtracks. Birdtracks, Lies, and exceptional groups. This is an obscure reference to a popular movie from the 90s, Sex, Lies, and Videotape. And this, in parts, was pre-invented by the trick of fate. Roger Penrose is older than me. So he wrote part of this kind of notation in 71. I did it 5 years later. But today, lots of people do calculations this way because lots of people have to deal with tensors. So for example, we have a professor at Georgia Tech who only does tensors. all draw these pictures, and they don't call them Birdtracks, they call them whatever they feel like calling them. But that's what it is. And all I want you to know is if you actually have to do some calculations in group theory, it might be easier to draw pictures than to do these indices. Now, you know, most people don't have to do this, but if you do general relativity, or if you have to do particle physics, you're all forced to do it. Also, if you do any modern kind of condensed physics, quantum computing, entanglement, etc., sooner or later you realize all these symbols that I've been giving you, they are extra, you know, unneeded. They get in the way of understanding relations. It's much easier to draw them.